Oh, there's two
Alright,
fish there.
we're going to review the first two sections of Chapter 6 are reviewing some algebra skills that we're going to be needing for this chapter and for next. We're still going to be focusing on triangles, but instead of looking at congruent triangles, like we have in the last couple chapters, triangles that are identically the same, just elsewhere on the coordinate plane, we're going to look at triangles that have a special relationship called similar. Similar triangles are going to be, we'll see a lot more properties as we go on in the next couple days. But today we're going to basically do a review of the algebra skills we're going to need to be successful in both this chapter and the next. Okay. The first is a review of a couple of algebra terms. The first is ratio, being a comparison of two numbers or quantities using division. Okay. Comparison of two numbers using division or quantities, whatever I say. Okay. We see there's three main ways that we'll see writing ratios. The two ways that we're not going to use that often would be comparing, say, A to B with a colon. Comparing A to B with the word to are the two less useful for us, or things we're not, well, not necessarily less useful, but less common, we'll see. And then there's the third way. Does anyone remember what our third way to write our ratio is going to be, Kate?
A over B.
Yeah, using a fraction. Is going to be our primary way to express a ratio, is a fraction. Word of warning, as we get into writing ratios as fractions, we see this more and more. Recall that our ratio is always still a comparison between two quantities. So if we simplify, say our ratio happens to simplify to a whole number, we definitely don't want to just write it as a whole number, because we'll lose that comparison piece between the two quantities. So if it happens to reduce to a whole number, then we want to express that as, say, that whole number over 1, so we still have the comparison idea in our ratio. To go along with we talk ratios, then the next kind of logical algebraic leap is to talk about proportions, which is two equal ratios, which we generally express as, say, A over B is equal to a second ratio, C over D. Okay. Ratio and proportions are pretty similar ideas. And then a proportion is an equation involving equal ratios. And then a ratio is just simply like one comparison, one of those sides is the ratio. Okay. And I'm gonna try to move kind of quickly through this again, since this is stuff hopefully you did in like 7th grade, let alone now in geometry. If we simplify ratios, it's very similar to reducing fractions. We're going to find numbers that are common amongst both of them. So if I want to reduce the ratio 64 to 6, Greg, what's that reduced to?
32 and 3.
32 meters to 3 meters. Absolutely. This would be the most simplified form if you want to leave your answers as what are called integers. You could create what's called a unit ratio. Remember the unit ratio? Yeah, it's when we write our comparison when we're comparing to 1. So you could write this as a unit ratio by dividing each of these now by 3. But notice this unit ratio would be either a fraction or a decimal over a repeating decimal. So rather than writing it as a fraction, we'll just leave this as just a reduced rate. Also notice in these cases my ratios have units. Your ratio better end with units too if you start with them. It's pretty important, especially when the units are different, like the second one, that we maintain what the original meaning was. Otherwise, the problem's kind of worthless. Simplifying this guy, we have 1 foot for every 4 inches. It's kind of cool.
So you don't have to like convert on inches?
You most certainly don't. One of the most kind of useful one of the most important uses of ratios is that we can compare. It allows you to compare two quantities that are of different units. So like kind of like the scale on a map that you've been seeing hopefully throughout like earth science so far and in the past. The ratio is just a scale, like a scale factor on a map is just a ratio of lengths. So it allows you to it allows you to make an intelligent comparison between like feet on a map versus inches, or inches on a map to like feet in real life or miles or whatever.
So, we're not gonna do that.
We see ratios we'll kind of talk geometrically a little bit here. Let's say the ratio of the angles of a triangle is 1 to 2 to 3. Find the measures of the angle. Well, we don't really know what the measures are yet, but we do know a couple important things. We know that they're ratios. If we took the sides and compared them, we have a side length. Like if this is the first side, then the second side is twice as long, and the third side is 3 times as long. We have a proportion here. Sorry, the angle measures. You're right. So one kind of strategy for taking a ratio and actually finding some actual lengths, if we know the proportions, might be to say, well, what if our first, since we don't know what, say, the first angle is, how would we say that's like x degrees? That's like angle 1. So what does that force, what expression does that force our second angle to be? Joel? 2x, because if this is 1, then our second angle's got to be twice as big, which would just be 2 of them. And then what's that force our third angle to be? 3 of them. Notice that the coefficients in front of the variables are the same as the ratio. It's the values of our ratio. Well, what else? Why did I create this? Well, what else do we know about this situation? Eunice? They need to add up to 180 because they're the angles of a triangle. The sum of the angles of a triangle is 180. So you could say x plus 2x plus 3x has got to be 180. 6x's is 180. X is 30. The question asks, find the measures of the angles. So then what is this? Knowing that x is 30, what's it force the angle measures of our triangle to be? Page.
30, 60, 90.
30 degrees, 60 degrees, and 90 degrees. Let's play a similar game with this perimeter. So I have a perimeter of a room is 48 feet. So if I drew myself a little picture here, I have the perimeter of this room, and the distance all the way around is 48 feet. And I don't know what the length and the width are, but I do know that their ratio is 7 to 5. So this is the length, and this is the width of my room. I know that the ratio of these things is 7 to 5. Well, we can play a same game, kind of a similar game, to get an expression for the length and width as we did up here with these angle measures. So if I took this ratio and created, well, I don't know exactly what the measures are, but I do know if I multiplied each of those by the same number, by the correct same number, then I'll get the actual length and width. Well, I don't know what that number is I'm going to multiply each of them by. So what I'm going to do is I'm going to call what that scale factor, whatever I'm going to multiply each by, I'm going to call that number my variable. I'll call that, say, x in this case. So if I say the width then is, and the length are then, well, I don't know what, but I'm going to multiply 7 and 5 by something. Or if I say length is, say, 7 x's, and the width is, say, 5 x's. Once I figure out what this value for x is, I can plug it in and get the actual length and width. And what's nice is since I'm multiplying each of these by the same, then their ratio is always going to be this 7 to 5. Well, I have a perimeter, and I have this information. What kind of equation can I set up to actually figure this stuff out? Paige? Yeah. Absolutely. I know the perimeter is twice the length plus twice the width. Or since I have expressions now involving x, I can do a clever substitution here. And get 2 times 7x's plus twice of 5x's. This is now 48. And solve this thing. So 2 times 7x is what? 14. 14x's. 2 times 5x is 10x's. This thing needs to simplify to 24x's. Therefore, x is 2. So if x is 2, what's the length and width of my sides here? What's the length? 14. Width is 10. Notice that 14 to 10 is the same ratio as 7 to 5. 14 to 10 is equal to 7 to 5. Therefore, my problem actually does make sense. Feet. Any questions thus far on ratios? All right, so let's transition to proportions. Does anyone remember what our main strategy is going to be for solving a proportion, where we have, say, 2 equal fractions? Cross multiplying. Our main strategy for solving a proportion is to be cross multiplying. Recall that our general strategy for proportions, if it's a to b equals c to d, then that implies that a times d is equal to b times c. And solve. We could get x is, in this case, say 10x equals 80. This is 8 by cross multiplying. By cross multiplying. Kind of a word of caution when we're cross multiplying is that before you do the cross multiplying, I recommend, especially if you have a binomial or anything more than just a monomial, on either numerator or denominator, so throw them inside of parentheses. So when we cross multiply, we remember that it's going to be 2 times y plus 1. So we don't make the easy mistake of 2 times y plus 1. It's supposed to 2 times the whole quantity, and we distribute. Otherwise, you get a kind of random result. Moving along. We're gonna also. Has anyone ever heard or seen of the geometric mean of 2 numbers before? Anyone ever heard of the geometric mean of 2 numbers? Okay, so it's a brand new thing. Awesome. Okay. You should be familiar with what's called the arithmetic mean. The arithmetic mean being the standard mean, the average of 2 numbers. It says arithmetic mean being the average via adding and subtracting. Okay. The arithmetic mean you get by adding your 2 numbers together and dividing by 2, or dividing by however many there are. The geometric mean we're going to get in kind of a more multiplying fashion. The geometric mean between 2 numbers is the product, or excuse me, the square root of the product of 2 numbers. Okay. In general, we'll create the arithmetic mean in the following fashion. We'll take, for our 2 numbers, a and b, the geometric mean is found in the following way. Whatever one of them is, divided by the geometric mean, is equal to the geometric mean over the second number. So if x is the geometric mean, of A and B, then we find it in the following fashion. We'll say take one of the smaller, or one of the numbers divided by x is equal to x divided by the other number. Okay? Notice when you solve this, when we cross multiply and then solve, you get x squared equals a times b, or x is the square root of a times b. The square root of the product of two numbers is defined to be the geometric mean. Okay? So you could do either way. You could find the geometric mean in either fashion. This proportion method for finding a geometric mean is going to be very important for us. Maybe not on this chapter, but we're going to review it again when we come back from holiday break and we look at chapter 7, because we're going to be spending quite a bit of time looking at some segments that we'll create in triangles, and specifically we'll notice that the geometric mean is pretty important as far as finding some missing quantities. Okay, and we're going to set up ratios using the geometric mean. So you have there is a formula if you just have two numbers. Here's the formula for geometric mean. However, if you have maybe a better way to find it might be to set up a proportion and solve. So if I ask you to find the geometric mean of two numbers, then we could say, how about 24 is to the geometric mean, as the geometric mean is to 48. Cross multiply and solve. You get x is the square root of, was it 1156? Was it? 52. 1152. Which is approximately, was it 30? 33.94.
Does it matter which way you put the numbers? Could it be like 48 over x is equals x over 44?
Yeah, we're going to see this actually, these other properties, there's actually two of them. One of them is that if even a proportion, if you have a proportion, then an equal proportion is just flipping on a diagonal. So yeah, you could if you want. Okay. 2 and 8. Well, find this geometric mean. You get what? 6, I believe. 2 and 18. Excuse me. I believe it's 6.
So because you get plus or minus 6, you just basically eliminate the.
Yeah. So when you solve this, we're gonna go with the positive square root. It's the geometric mean is meant to describe. It describes an average between two numbers. So if we went with the negative, then we're not getting. Then you get a number that's not between these two. So it doesn't really measure an average for us. Right? Okay. Two other properties of proportions, and we'll call it good for today. Our first property says that if the following is true, if you have a proportion, if this proportion is true, then you can actually rearrange this proportion in two main ways. And it's predicated on the idea that when we solve this, all we're doing is cross multiplying. So I can rearrange, you can rearrange this proportion. If you know this proportion is true, then the following two proportions must also be true. If I flip one of them along the diagonal, I get the following proportion. Then you could say D over B is the same as C over A. And also, you could flip both. So if I flip these two and these two, you get the following. You get D over C is equal to D over C is equal to B over A. Be two new proportions you can create based on the original. Okay. Notice that all three of these, how do we solve any of these proportions? What's your strategy for solving proportion? Cross multiply. So when I cross multiply each of these three things, you get the same expression. You get A times D equals B times C. A times D equals B times C. A times D equals B times C. You get the same value. So the proportions are true. Okay? You can rearrange the ratios based on the idea that you're just going to cross multiply. The second property is kind of less intuitive, but I do want to go through a quick like algebraic proof, I guess, of why it's true. Here's the. Don't panic when I say the word proof, please.
We just too late for that.
If A over B is equal to C over D, then the following proportion is also true. If this is true, then you're allowed to add the denominator, or really any multiple of the denominator to the numerators, and you still get a true proportion. Okay. I'd like to explain kind of where this comes from. This is not just like out of the dark. This proportion comes from the following. Comes the following way, and I'll explain on this sideboard here. Actually, we're going to start with. I'm going to go through a quick algebraic proof of why this is true. So if you we're starting under the assumption that this works, that A over B is equal to C over D. Okay. Would you agree that I could add the same number to both sides of that equation and still balance? Yeah. Okay. I'm going to add the following number.
A 1 or a 7?
It's a 1.
Okay.
You could add 7 if you wanted, but the proof's less. It's easier if you use 1. Okay, assuming that this works, I'm going to add 1 to top and bottom. Or excuse me, I'm going to add 1 to both sides. So this is still a balanced equation. Okay. Now I need to figure out how. Now the next thing is to do is to combine this expression and this expression into just one fraction, as opposed to two separate terms. Okay. So now you got to dig deep into your knowledge of fractions. I'm going to combine each of these into one fraction. So we got to dig deep and think, how do I combine two terms that don't have, how do I add these two expressions together? How do I add this fraction to this whole number 1? What do I need to do first? What do I, thinking more in general, what do I need to have happen in order to add a fraction to something else? Someone said over here, common denominator. So I need to get both of these so they have the same denominator. Well, how do I add a fraction to a whole number? Well, I better put it over 1. So I even so I build a fraction first. And what number what's the smallest number in common between B and 1? Whatever this thing is. What goes into both. Whatever this thing is. Any number I can if I multiply 1 by, or another way of thinking is, what can I multiply 1 by to make it this? Whatever this is. Whatever B is, I'll multiply it. Okay? So I'm going to multiply to get this as a common denominator. To get this as a common denominator, I'm going to multiply the bottom by this number and the top by it as well. So I get this thing. I get A over B plus B over itself. Notice this is 1. Something divided by itself is 1. Equals C over D plus, we'll do the same trick. This expression, anything divided by itself is just 1. Now I have a common denominator. So now I can actually add these expressions together. When we add fractions, we keep the denominator and just add the numerators. Well, these are not like expressions but that actually gets us where we want to go. Is A plus B actually the same reason. So keep the denominator, add the numerator, which is exactly the expression we had in the front side. Okay. So in particular, this thing is not just comes out of the blue. I did not just make this up out of nowhere. This actually derives from algebraic reasoning. This actually is true. Okay. So, and in fact, you can actually generalize this, and you can add any multiple of the denominator to each side. Why do we go through this? Because we're going to hopefully you'll be able to use this to recognize new proportions that we'll build. So for example, if 6 over x equals 24 over y, this is my original proportion, then I'm going to write a new proportion in the following manner. Then 6 over 24 should be equal to what over what? Well, we can think about how did I go from this proportion to here? X used to be down here, now I have a 24. So if I want to create an equal proportion, I could just flip along this diagonal. So if I flip the 24 down, I'm bringing the x up above. So 6 over 24 should be equal to x over y. Notice I just flipped here. You could check to see this is true, because if we cross multiply the first one, we should get the same expression as we cross multiply the second one. 6 times x, 24 times, 6 times y, 24 times x. 6 times y, 24 times x. Good. In the second one, here's my original proportion. What did I do to go from this proportion to this expression? What do we do? I add the denominator. So then what should my second fraction look like then?
5 plus 5 plus 11, which is 10. Oh.
Should be 5 plus 11 over 11, which is 16 over 11. Will be another proportion when you write it. Last but not least, I have this not to scale drawing, but this is the direction we're headed. When we're looking at what are called similar triangles, we're going to see some proportions we're going to build. In this case, I'm not going to ask you to know how to set the proportion for yourself. I'm just going to tell you what it is, and we're going to solve this proportion by doing some substitutions. And hopefully, some of you jump to the end and figure it out already. If S over R, if SR over RQ is equal to ST over TU, what's this length here? Yeah, we could get 8. Hopefully, we could get 8. You can set the proportion up. You could just substitute these values, and you get 3 over 4 equals 6 over something. You could cross multiply and solve. One way would be 3x. X is 8. Some people, maybe you reason that if here's a proportion, how do I go from 3 to 6? You can find what's called the scale factor. I go from 3 to 6 by multiplying by 2. So I can go from 4 to x by multiplying by 2. 4 times 2 is